Hello and welcome back. This is video 1 of 2 for Chapter 10. Now, Chapter 10 is a sort of all-encompassing chapter on basic DC circuit analysis. And in this video, what I'd like to do is to first talk about resistors in series and parallel, much like we did with respect to capacitors. And then I'm going to show you some voltage and current rules that are used and are incredibly useful for circuit analysis in general. I'm also going to include something called a loop rule, which is a method you can use to solve more complicated circuits, in many cases ones that have, say, more than one power source. So that said, what I'd like to start off with is a discussion about batteries in general. Because in DC circuits, we typically think of a battery as being the thing that supplies the power. But batteries are actually relatively complicated devices. As I mentioned in previous videos, in general, they're electrochemical in nature. You know, you have things like lithium-ion batteries and what have you. But if you were to think about a battery itself, inside a battery, we basically have two things. So the first thing that you have is what we call electromotive force. Now, the electromotive force would be the voltage that's associated with the actual chemical reactions. Typically in a battery, you have something called an anode and cathode, which have, differing potentially, signs. And so, on one of them, positive charges are attracted. On the other one, there's negative charges that are attracted. And the actual thing that's doing the moving there, the potential difference that's doing the moving of the ions inside the battery, we call EMF. Usually it's denoted sort of with a cursive E that looks like that. Now, likewise, inside a battery you have an innate amount of resistance. There's a small resistance in there. So if you think of batteries supplying current, and you think of Ohm's law, which is was the subject of the previous chapter, where you have V is equal to I times R. The voltage that you get at the terminals really is a combination of the electromotive force that you have present and a small loss that's due to the innate resistance of the battery. Okay, so the real driver of charge around a circuit is this EMF stuff. It's just sort of hopelessly mixed up with resistance before you are able to get it, from the terminals of the battery. So V usually refers to the battery's voltage, but EMF is what's going on the inside. So just, now that we have that clarification, what I'd like to do next is to take a look at resistance in different configurations. If you remember, we did this with, again with capacitors. And what I'd like to come up with are a series of addition rules based off of Ohm's law that that basically help us solve circuits. Now, just like with respect to capacitors, the idea here is to reduce your circuit in complexity. So here, what we would like to do ultimately is to reduce it to something that's going to look like a battery, with one, we'll call it an effective resistor that is, that encompasses whatever resistance is going on, involving these two that are in series. So, what we would like is to transition to something that looks like this. Now, thankfully, though, when it comes to dealing with resistors, things are actually pretty easy. So I want you to look at the battery here. We know that the short bar side is the negative side, the long bar side is the positive side, and we know the conventional direction for current flow is this way around the circuits in the direction from plus to minus. So if you think about current as water, as I mentioned, last chapter, what you have here basically are two crimps and a hose. So each one supplies resistance. But if you think about this as something that's flowing through, that's incompressible, then the amount of current that flows in this side right here is going to have to be the same amount of the current that flows out this side right here. It's just like a garden hose. So what that means is that if you think of the way current works in a series circuit with resistors, in a series circuit, the amount of current that would be flowing through R1 and the amount of current that would be flowing through R2 are going to be the same. So in a series circuit, the current flowing through components is the same. So it's somewhat analogous to voltage in parallel circuits, where the voltage is the same across all the components in a parallel circuit. Here, the current that flows through is the same through all components in the series circuit. Now we can use this to our advantage, because what we want to do, like I said, is to reduce this complexity where these two resistors can be sort of replaced by one. So here, if you think about it, in this particular configuration right here, Ohm's law says, V is going to equal to whatever the current is, I, and whatever this effective resistance is, which I'll call R effective. Now, we also know, according to what we learned about voltage, in a series circuit, the voltage across each component in your circuit adds up to the whole. So what that means is that V itself is what you get when you add up the voltage across the first resistor to the voltage that's across the second one. And if you look at Ohm's law here, that's the same thing as the current. It's the same current flowing through both of them, I times R1 plus I times R2. Now, this right here is our source voltage, it's the total, and like I said, what we want to do is we want to figure out how to replace those resistors with 1, and so it would be equal to that. And as you can see, the currents, they cancel. So in a series circuit, the resistance just adds, which should make sense if you think about it, from a garden hose standpoint. So this is in a series circuit. Okay. Now in a parallel circuit, it's a little more complicated, because what you have is you have these splits in the wires right here. You have these junctions. And so if you think of this as sort of like being one of those little Y junctions on a hose, if you turn it in the center, some water is going to flow through one side of it, some water is going to flow through the other side of it. So here, if you think about this as being the positive side and this being the negative side, when your current here starts from the battery and begins to flow this way, some of it's going to go this way and some of it's going to go this way. So I'm going to call the part that goes down here, since it's going through R1, I'm going to call that I1. And the part here that's going through R2, I'm going to call that I2. Okay. Now, this is going to flow around. So here's your current flowing around. So this is I2 and this is I1. And when they meet at this junction right here, they're going to combine to give you the same amount of current that went in, out. So what we know here is that your total current I is going to be what you get when you look at the current that goes through each one of the junctions. So in this case, I is just equal to I1 plus I2. Now again, we want to take the same approach here. We want to replace this in complexity or reduce this in complexity rather, to something that just looks like one resistor, kind of like this, R effective, with the same source voltage. So the difference here is that now your components have different currents, but the voltages here, since this is in a parallel circuit, are the same. So what that means is this V right here is the same as the V across here is the same across the V right here, because we know in a parallel circuit, the voltages are the same because wires are regions of equal potential. Okay, so what that means is that if I think of Ohm's law as being V is equal to I times R, I can write my current equation here as I is equal to V over R. Okay, so if I were to put this into this, my source volt, or my source current, or rather my source voltage with this replacement right here with R effective is going to give me the total current that's going in here. So that would be the source voltage R over R effective. And on the right hand side, I1 is going to be V over R1, and I2 is going to be V over R2. And again, in a parallel circuit, the voltages are the same, so they cancel. So here, what you have is 1 over R effective is equal to 1 over R1 plus 1 over R2. And, it's just like capacitors, but in reverse. So this right here is what you have in parallel. So we also have, a statement about current in parallel circuits as well. And that's the current as it passes through and recombines at junctions adds up to give you the whole. So current adds in a parallel circuit in much the same way that voltage adds in a series circuit. Okay, so you can literally write up a whole bunch of laws here that are useful, or rules. And so in series circuits, here's what we know. The first thing is that voltage adds to the whole. So what that means is that the voltage across each component, okay, the voltage across each component adds up to give you the total voltage, and that's a consequence of conservation of energy. The second thing we know is that the current is the same through all components. Now, we also can say things about resistors and capacitors, but I'm not going to do that here. Okay, these are strictly going to be laws of voltage and current for right now. Now, in a parallel circuit, we know that the voltage is the same across all components. And it's the same as the source voltage. We also know that the current adds to the whole. That means that, the current, when it passes through a junction, is split. When those junctions recombine, you get the same current out that went in. Now, in part, that's a consequence of conservation of charge, which is something that you learn about in different class. So what we have here are a series of laws that we usually call Kirchhoff's laws. Kirchhoff's voltage and current laws. Okay. Now, so that said, what I'd like to do is to take a look at this circuit right here and reduce this in complexity in the same way that we reduced a capacitor circuit. Okay. Now this is a pretty complicated one, but what we're going to do is we're going to treat this in much the same way that we dealt with capacitors. We just take steps. And the first steps that I want to handle are these right here, where you have these components that are in series with each other, R2 and R3. So what I'm going to do is I'm just going to write down what I've been given here. And we have 7 resistors. R1 is 4 ohms. R2 is 4 ohms. R3 is 8 ohms. R4 is 10 ohms. R5 is 4 ohms. R6 is 2 ohms. And R7 is 2 ohms. Now we also have a source voltage of 5 volts. And what I'd like to find here is the voltage across and current through. The components. Okay. Now this is a fairly complicated example, but as we're going to see, it actually reduces relatively easy. And we're going to use, like I said, these voltage and these current laws to help us do this. So the first thing I want to do is to reduce this in complexity the following way. So what we're going to do is we're going to take R2 and R3 and combine them into a resistor, and take R6 and R7 and combine them into a resistor. So our first step in complexity reduction is going to look like this. So that's the first resistor right here, R1, and then this is 2 and 3 combined, which I'll call R2, 3. Then we have R4 right there. We have an R5. Right here. And then what I'm going to do is I'm going to combine these two right here into R6 and 7. Okay, so just for notes here, R2, 3 are resistors added in series, and we know here that when you add resistors in series, you just add them together. So R2, 3 is going to be R2 plus R3, which is going to be 4 ohms plus 8 ohms, or 12 ohms. All right. Now R67 is going to be the same. R67 is going to be R6 plus R7. So you add it the same way, but in this case it's 2 ohms and 2 ohms, which is 4 ohms. Okay, so we've reduced this complexity. The next thing we're going to do is to take R67 and R5 and add those two together, but we're going to do it in parallel. Okay, so our reduction in complexity is going to look like this. That's R1. This is R2, 3. Then we'll have an R4, and this would be R5, 6, 7. So what's R5, 6, 7 going to look like? Well, you know, in that case, you're adding these things together in parallel. And we know that when you add resistors together in parallel, you do it reciprocally, like, you know, with capacitance in series. So here, R5, 6, 7 is going to be 1 over R5, or 1 over R5 rather, plus 1 over R67. So if you plug the numbers in there, R5 is 4 ohms. R67 we found to be 4 ohms. So this would be 2/4 ohms, or 1/2 in the bottom, and when it flips up to the top, you get 2 ohms. So you'll notice that this is almost, we're starting to almost run into a bookkeeping issue. So what I like to do at this point usually is to sort of keep track of stuff. R23 is 12 ohms. R67 is 4 ohms. R567 is 2 ohms. Okay, and that way if we need to, we can erase. And so the next thing is going to be to take this and to reduce it in complexity by adding R4 and R567 together. When you do that, you're going to get this. Here's R1. Here's R23. And then you'll have an R4, 5, 6, 7, which is these two added together in series. So R4, 5, 6, 7, I mean, they're in series, so that's just R4 plus R5, 6, 7. R4 is 10 ohms. R567 is 2 ohms. So that's 12 ohms. So let's keep track of that. R4567 is 12 ohms. You see how this is just reducing in complexity from this big ugly thing into this, into this, into this. And we really only have 2 more steps to go. The next step is going to be to take it and reduce it this way. There's your R1. R2 and R4, 5, 6, 7 are in parallel to each other. So we're going to add them together that way to give us a effective resistance there of R2, 3, 4, 5, 6, 7. It's pretty big. Okay. But again, you know, they're in parallel. You know, here. So, you know, R2, 3, 4, 5, 6, 7 is going to be 1 over R23 plus 1 over R4, 5, 6, 7. And, you know, R23, we got that here. It was 12 ohms. R4, 5, 6, 7 is 12 ohms. So it's going to be 1 over 12 ohms plus 1 over 12 ohms. So here again, you know, this would be 2/12. 2/12 is 1/6. When it flips to the top, it becomes 6 ohms. So that's, woo, went up too far. That's a lot of writing. So I'm going to call this R2 through 7. And that's just equal to 6 ohms. Okay. So this is R2 through 7. So R2 through 7. And finally, we have these resistors that are in series. So your last reduction in complexity gets us to our overall effective resistance. R effective, which in this case is just going to be R1 plus R2 through 7. You just add them together. So R1 was 4 ohms. R2 through 7 is 6 ohms. and that's 10 ohms. So we've reduced this thing entirely. So now, having done all these reductions, what I'm going to do is to clear a little bit of this workspace. We're going to need these steps here to help find the currents, because we're going to talk about where the currents are here in a moment. But let me just sort of clean this up a little bit so I have a work area here. Actually, I can just do this. Bam, gone. Whoops. I was hiding there too. Gone. Okay, so let's talk about the current. And we're going to start with the total current, okay? Because what I like to do is to sort of show how the current flows here. So the total current leaves the battery like this, and we're going to call the total current I. So here's I entering this junction right here. Now when it enters the junction, it's split. Okay, so some of the I goes this way, and some of the I goes this way. So I'm going to call the part of the I that goes this way I 2, 3, because it's going through 2 and 3. And I'm going to call the part of the I that goes this way I 4 through 7, because that's going to end up going through all this stuff over here in some way. Now, at the end of the day, whenever it's done doing its thing, what we expect to happen, since this is the node here where everything combines and goes back into the battery, is I expect this to be I 4 through 7 re-entering this way, and then entering this way over here, I 2, 3. So when it exits over here, my current that's coming out is going to be I 2, 3 plus I 4 through 7. Okay, so we expect that to be true. So that's going to be one relationship that's important. The total current here is going to be I 2, 3 plus I 4 through 7. Now let's talk about I 4 through 7, because it still has another junction to hit. And so what happens is I 4 through 7 hits this junction, and some of it split this way. We'll call this I 6 and 7 because it's going through these. And then, some of it split this way. This is I 5 because it just goes through 5. But again, just like over here, as this goes through here, when it gets out and hits this junction to exit back over here, this is going to be I 6, 7. And this right here, when it comes through, is going to be just I 5. So we expect, again, I 4 through 7 to come out. So what we have here is that I 4 through 7 is really just equal to I 5 plus I 6, 7. So there's another relationship. So there are some, voltage relationship or some current relationships. Now, we'll talk about voltage here in a moment. Primarily, it's, here you're going to have it in series. Here you're going to have it in parallel when you look at how it's distributed across. And the way to figure out how we're going to handle that is going to be to look at our circuit as has been reduced in complexity, but we're going to do it backwards. So here's what I mean. So we're going to start here with the most basic analysis that we did here. This is the source voltage V, and this is R effective. So this is going to give us our total current, I. So what we found out was that we have a source voltage of 5 volts, and our effective current, or effective resistance rather, is 10 ohms. So here, this is 5 volts, this is 10 ohms, which means that my total current, okay, is just going to be V over R. because V is equal to I times R, R effective. So here it's going to be 5 volts divided by 10 ohms, or 0.5 amps. So the total current that is leaving this battery and passing ultimately in some form through all these resistors and stuff like that is about half an ampere. So I'm going to note that here, that my total current is 0.5 amps. Now, so the next reduction in complexity that we took went from this to this. So now let's take a look at this. Now in this configuration we have 2 resistors in series. We have R2 through 7 and we have R1. Now I know that in a series circuit like this the voltage adds. So what I would have, it would be a source voltage V. I would have a V1 here, and then I would have a V2 through 7 which handles the rest of the components. Ultimately, how it does that we're going to find out. So what this tells me is that V here is going to be V1 plus V2 through 7. Now, how do we get the voltages? Well, again, you go and you look at the series and the parallel laws from Kirchhoff. So in a series circuit, which is what this reduction in complexity gave us right here, in a series circuit, voltage adds to give you the total, and the current is the same through all the components. So that's the key there, is the current's the same. So we know V is equal to I times R. That's Ohm's law. So what that tells us is that V1 is going to equal to I times R1. And V2 through 7 is going to equal to I times R2 through 7. So we found our source current. Our source current was half an ampere. And R1 we were given as 4 ohms. So half of 4 is 2 volts. Okay. So what I'm going to do over here is to create a chart. And I'll say component voltage and current. It'd be helpful to spell current right. Now our components are R1, R2, R3, R4, R5, R6, and R7. So let me draw some lines here to separate this. And many people, when they do this, they print worksheets to do this. So you may find that to be useful, where you just sort of get into Excel and make some columns and some rows with the titles that you want for a particular problem, and then just sort of fill stuff in. It helps you order it, because there's so many components that organization is frequently an issue with this. So what we found here, and I'll just for brevity put total here. We have 5 volts at the source. We have an R effective of 10 ohms, and we have a total current of half an ampere. Okay, so what we found over here doing this was the voltage and also the current through R1. The voltage is 2 volts. The current is the original current that we started off with here. It's half an amp. So here, from a voltage standpoint, it was 2 volts, and from a current standpoint, it was half an amp. Okay. Now, so let's take a look at our problem again. Here, what we did was to find V1. Now we have V2 through 7. That's going to be half an amp times whatever R2 through 7 was, and R2 through 7 was 6 ohms. So that is 3 volts, which is what we expect. We expect it to be distributed across to add up to the whole, so 3 volts. So nothing we can add in here because these are individual components, but what we do have is useful information, because what that tells us, if you look at the next step backwards in complexity, is that the voltage across this was V1, but the voltage across this right here, okay, is V2 through 7. Now that's pretty big because this is, if you just look at this part, because we've already found out what we needed about this one. We found it out here. So this has already been done. So what I'm going to do is to X this out. This has been done. Okay. So what we have here are 2 components in a parallel circuit. And again, we have rules for parallel circuits. The voltage is the same across all components, and current adds to the whole. So if I go here and I look, it's basically the same thing as what we're looking at here. Okay. So here we have, in this particular reduction of complexity, our current I going in. We have an I23 going this way. And then we have an I 4 through 7 going this way. Okay. I 4 through 7 right there. So we know this though. We know that through these components right here, the V is the same. So V23 and V4567 or V4 through 7 are going to be the same, 3 volts. Here. Three volts across this as well. Now let's talk about the current. Okay, because, you know, V is equal to I times R. So V23, which we know, it's 3 volts, is going to equal to I23, which we don't know, and R23, which we do. So I23 here is V23 over R23. V23 we found was 3 volts, and R23 we found solving it is 12 ohms. So this is 3/12 or 1/4 of an amp. So 0.25s. So this is the current through both component 2 and 3. Because remember, we reduce these in complexity. And as a consequence, we'll be able to find V2 and V3 using that. So let's go ahead and do that. So I23 we found was 1/4 of an amp. I'm just going to write it this way. So we have, just in this little part, in this leg we say, 2 components that are in series. The current is the same through both of them because it's in series, but the voltage adds up to the whole. What's the whole? Well, that's going to be I23 or 3 volts. So if I follow the same Ohm's law stuff that we did for our reduction in complexity here, noting the fact that we know what I23 is, finding V is pretty easy because we know what R2 and what R3 are. So V2 is going to equal to I23 times R2, which is 1/4 of an amp, times R2. And what's R2 equal to? 4 ohms. R3 incidentally is equal to 8. Let's remember that. Or, when you do this, 1 volt. V3, I23, R3, 1/4 of an amp times 8 ohms, or 2 volts. 1 plus 2 is 3. So it adds up to what you expect. So now we have some more useful information we can put in our stuff. So R2 and R3 both have currents of 0.25 amps. 1/4. Their voltages are different. We found them to be 1 volt across across R2 and 2 volts across R3. So you see how this is starting to get filled in. It's all about reducing the complexity and working backwards. So, done quite a bit. We've done some complexity reduction. What I'm going to do is to clear up my work area here. Since we've already done this right here, let's get rid of that. Let's get rid of this. Let's get rid of this, just making some room. These are things that we can look up. We've done part of this. We still need to do R4, 5, 6, 7 and find its current. We found the current going through R2. So what we do know is that, looking up over here, the current that enters, the part that goes down here, if you add that to the part that goes here, well, they're going to have to be equal to each other. And here is I23, which is this right here. So I is going to equal to I23 plus I4 through 7, which means that I4 through 7, which we're going to need to talk about this next step over here, that's equal to I minus I23. Now I, remember, was half. I23 was 1/4. So 1/4 of an amp. So what we know here now is that I4 through 7 is going to be 1/4 of an amp here as well. Okay, 1/4 of an amp. Now let's work backwards in our reduction of complexity, because we know the voltage across this and the voltage across this is the same. What that tells me is that the voltage across these components right here, these two right here, this is 3 volts as well. Remember, originally it was in parallel. So you can treat this almost as though it's the source voltage, which means that some percentage of the 3 volts is going to be across here and some percentage of the 3 volts is going to be across here. We also know from the previous part how much current is flowing through this part right here. How much is it? It's 1/4 of an amp. Now we have two resistors that are in series with each other, and finding their properties is very easy. Because it's just simple Ohm's law. For example, I know V4 is going to be, V is equal to I times R. That's going to be I4 through 7, since that's the current that's running through it, times whatever its resistance is. Well, I4 through 7 is 1/4 of an amp. The resistance of component 4 is 10 ohms. And, what's 1/4 of 10? 2.5. Okay, so 2.5 volts is going to be going through, or is going to be laying across this guy right here. Now, so if you have 3 volts going across here, you have 2.5 of it going across that. What that means is that the remaining half is going to be across this. Okay, so half of a volt. So now we just found out more information we can put in our table. We have the current and we also have the voltage, 2.5 volts and quarter of an amp. So again, gradually filling out our table. Next, we're just going to keep working. We're going to keep working back. So going from here to here, R567 is this right here. It's this thing right here. Okay. What I'm going to do is to sort of drop this right here so I can work below it. And I'm going to get rid of that right there as well. So, so again, you know, we found out that the voltage across 567 was half a volt. So here, half of a volt right there. And this is in parallel, which means that you're going to have half a volt across this, and you're going to have half a volt across this. So now we know the voltage across both of these components. And, you know, since these right here are in parallel to each other, that means we can very easily find the current that goes through this and also the current that goes through these as well. So let's do that. So, you know, the voltage, like I said, is, we'll call it V567, is across here. And that tells us that R5 experiences the same voltage as well. And since V is equal to I times R, that means that I5 is going to equal to V567 over R5. So V567 is half a volt. R5, if you go over here and you look, is 4 ohms. That's a half times a quarter, which is an eighth. So that's going to be 1/8 of an ampere. Okay. So here's what we have. We have the voltage across in the current through component 5. Half of a volt, 1/8 of an amp. And that leaves us just 6 and 7. Whoops. 6 and 7, as you can see here, are in series with each other. And so what we have is we have voltage that goes across them, same voltage as over here. So the voltage, we'll call it V67, is half of a volt as well. So really, if you think about it, the current that's going through here it doesn't change, but the voltage is being distributed across here. So this is I67, and the thing is we just found I5. So we know what I5 is. We know the current going in, that was I4 through 7. I4 through 7 was a quarter of an amp. So I67, well, rather the relationship between them would be, you know, I4 through 7 is equal to I5 plus I67, right? So here I67 is equal to I4 through 7 minus I5. I4 through 7 is a quarter of an amp. I5 we found was 1/8 of an amp. The common denominator is 8, so that would be what was that? 2/8 minus 1/8, so an eighth. Okay. And so there we have the current going in. We have the voltage across both of these, because the voltage across both of these again is you know, half a volt across both. I67 we found to be 1/8 of an amp. And now it's just Ohm's law to find the voltage across them. So, V6 is going to equal to I67 times R6. V7 is going to be equal to I67 times R7. And R6 and R7, you look here, R6 is 2 ohms, R7 is 2 ohms. So this would be, 1/8 of an amp times 2 ohms, 1/8 of an amp times 2 ohms. And, this is a quarter. 1/4 of a volt. Whoops, 1/4 of a volt. So they both have the same amount of current going through them, 1/8 of an amp, and they both have the same voltage across them because they both have the same resistance, and that's 1/4 of a volt. So, 0.25 volts and 1/8 of an amp. And there you go. We have fully analyzed the circuit. Okay, it's a pretty complicated circuit, but we found, the voltage across and the current through all of the components present. And, the biggest thing here is making sure that you go through and reduce the circuit all the way back to, it acting as though there's just one component here. And then what you do is once you find, the properties of that, the effective resistance, we'll say, and the total current, then you move forward in complexity until you get back to your original circuit, finding, the currents going in and out of junctions at each step and the voltage across each component at each step. Now that said, what I'd like to do, just to sort of mention, and it is a very useful tool, is to talk about something called Kirchhoff's loop rule. Now, Kirchhoff's loop rule is based off of conservation of energy, and it's a way of dealing with circuits that, may be complex, in which you can exploit it. Like, for example, this right here, we could have potentially used Kirchhoff's loop rule. As to whether it would have been easier or not, it's arguable. And here, where we have multiple sources, because we have 2 batteries here. Now, let me explain to you how the rule works. What you're looking for are closed loops. So I see 3 of them here. I see one closed loop right here. I see one closed loop right here. And then I see a big closed loop that goes like this. Okay. So the idea is that if you think about this from a conservation of energy standpoint, if I were to leave the battery, noting the energy that the battery is putting out, and then subtract away each little bit of energy that I give up, when I get back, I should get equal. I should get 0 because I should have used up all the energy. Okay. Now there are rules to this, if you will. So remember, the long bar on a battery is positive, the short bar is negative. The long bar is positive, the short bar is negative. Now the rule is this: when you walk around the loop, the first thing you do is to walk clockwise. Now, in part, it's this clockwise walk, noting the directions of currents as you hit nodes, that allows us to relate the loop that you start off with to the rest of the loops. I'm going to show you how that works here in a moment. Now, the second rule is this: going from negative to positive in that direction across the battery, from negative to positive, the battery adds in is positive. If you go from positive to negative, the battery adds in as a negative. Now, what I'm going to do is to show you the three equations that you get walking around this loop. And then I'm going to put some numbers in for our batteries and our resistances here. And so, um, so let's start off following these two rules right here. And we're going to start from our battery, which I'm going to call B1 as per the image right here. So starting off with B1, B1 is positive. My first loop is going to be this one right here. So as I go around my circuit, going this way, this is the direction, okay, I passes through R1 to take away some energy from that. As I keep going, that I is split this way. This direction I'm going to call I2, and this direction right here I'm going to call I1. Just choosing numbers or subscripts. So as I go around here and I get to this loop right here, I have I1 going through R2, taking away some of this energy. Remember, this would, V is equal to IR. This is a V as well. Okay, they're not the same, but that's what they are. V1, and we'll call that V2, if you will. When I get back here, I've used up all my energy, and I am at 0. Now, so that's loop 1. This right here, this is loop 1. My next loop that I want to choose is going to be this big loop. Again, going this way like that. Starting off with V1, going this way from negative to positive is positive. Going through this, again, I, R1. Continuing through around my loop. You might ask, why are you neglecting the center? Well, the center isn't a loop. This is a loop. The center breaks up the loop. Going this way, I have I2, R3. It's going through, so it's taking away. That is, the current is going through in the direction that I'm traveling. Then I come across this battery here. Oh, look, hold on. This battery, now when I go across this battery, I'm going from positive to negative. Now, the rule for that is that it adds in as a negative. And then when I get back over here, I'm at 0 again. So that's two equations. Now, you can get a third equation by looking at this loop right here. So like I said, 3 loops that I can see here. You may or may not need it. Since we have 2 currents, actually 3 currents that we need to find, it'd probably be useful to have 3 equations. So what I'm going to do is we'll go around this way. From the battery, remember we go clockwise around the loop. Clockwise is this way. Clockwise gives us a minus B2 because we're going from positive to negative. We're fighting against I1. Before, we were going with it, which made it negative. We're fighting against it. That makes it positive. I1, R2. Going back this way. Now we're going in the direction of. We're going with I2. Makes it negative. And then we're back to the battery, giving us 0. So now we have 3 equations and we have 3 unknowns. And really, all you're doing is just solving a set of linear equations, which is pretty easy to do. How you do it, it's up to you. You can use matrix reduction if you want to do it that way. You can just find one and solve for it if you want to do it that way. It's entirely up to you. But let's plug some numbers in to make it interesting. We'll call B1 is 10 volts. We'll call B2 5 volts. We'll call R1 5 ohms. R2 10 ohms. And R3, we'll call that one 5 ohms as well. Now, what I'm going to do is to find the current. If I can find the current, then I can very easily find the voltage across each component. I'm going to leave that up to you as an exercise. So, again, it's up to you how you want to do this. I see a relationship between I1 or I and I1 here. Uh, I have a relationship between I and I2, a relationship here between I1 and I2. And, let's not forget that as per conservation of charge, I is going to equal to I1 plus I2. So that's an established understanding with respect to how these junctions work. Okay. So, we really have 4 equations and 3 unknowns, which means that, we can sort of go with however we want to do it. And what I want to do is to, let's see here. I'm going to put this in terms of I1 and I2, and then use this in conjunction with this to find a relationship between I1 and I2 individually. So I is equal to I1 and I2, so I'm going to call this equation 1, this equation 2, and this equation 3. So we have B1 minus I is equal to I1 plus I2 times R1 minus I1 R2 is equal to 0. So if you do a little bit of math here, sort of simplify things, and let's get the I1s and the I2s by themselves. I have B1. This is an I1 here. It's negative. This is a minus I1 here. So this would be minus R1 plus R2. I1. That takes care of this and this part right there. And then what I'm left with is a minus I2 R1. And that's equal to 0. Okay. So you have this equation. This is equation number 1. And then we have equation number 3, which deals with I1 and I2 as well. So equation number 3 says minus B2. So again, this is 1, and this is 3 right here. Minus B2 plus I1 R2 minus I2 R3 is equal to 0. And how you decide to approach this is entirely up to you. So what I'm going to do is I think probably the easiest way is going to be to take this equation right here and solve it, we'll say for I1, and then plug it into here, and then when I turn the crank, that's going to give me what I2 is. And then I can use this and get I1 from it. So if I solve this for I1, what I'm going to do is to move B2 over to the right-hand side and also move this over to the right-hand side. I have I1 R2 is equal to B2 plus I2 R3. Now I'm going to divide both sides by R2. And that's I1 in relationship to I2. Now I can take and I can plug it into this right here, this equation they got right here for I1, and then the only thing I won't know there would be I2, and I can solve for it. So let me do that. Now I'm plugging this equation right here into this, actually into this explicitly right there. So that's B1 minus R1 plus R2 times I1. Now I1 is this. So that takes care of this. Minus I2 R1 is equal to 0. So I know everything here except for I2. It's just an issue of solving for it now. So what I'm going to do is to move this stuff over here to the right hand side and flip things around, leaving the battery on the left hand side, or B1 on the left hand side. When I do that, I have an R1 plus R2 B2 plus I2 R3 over R2 plus I2R1 is equal to a B1. Okay. Now, the goal here is to pull the I2 out and then have a bunch of gobbledygook over here that we can just plug stuff into. And the first step to getting there, I think, is going to be to multiply both sides by R2 and then to divide both sides by R1 plus R2. And when I do that, I get a B2 plus I2R3. That's this right here, plus I2. Now, it's an R12, or R1R2 rather, over R1 plus R2. So that's what I get when I multiply both sides by R2 and divide by R1 plus R2. And what that does also, since I'm doing it to both sides, is to affect the battery. That's B1 R2 over R1 plus R2. Now things are getting there. So now, if you look over here, I have this battery term floating around that really isn't attached to an I. So I'm just going to move that over here. So I have an I2 R3 plus an I2 R1 R2 divided by R1 plus R2 is equal to B1 R2 over R1 plus R2. This is all algebra. I mean, we stopped doing physics way up here where we're doing loops. And then I'm moving the B2 over here like that. And, now you could plug stuff in and, pull things out if you want to. I'm going to go ahead and pull the I2 out. When I do that, I have that left. And on the right-hand side, I have B1 R2 over R1 plus R2 minus B2. Now, what I'm going to do is just to go ahead and explicitly solve for I2 from an algebraic standpoint and plug my numbers in. I'm going to do up here because this is close to where my givens are. So I can just very easily reference them. But when I solve for I2 here, what I get is B1 R2 over R1 plus R2 minus B2 divided by a bunch of junk. That's R3 plus R1 R2 divided by R1 plus R2. And now you understand why they have circuit analysis software. You don't have to do that. And now it's just plugging stuff in. What's B1? That's 10 volts. What's R2? R2 is 10 ohms. That's divided by R1 plus R2. R1 is 5 ohms. R2 is 10 ohms. Minus B2, and that's 5 volts. Divided by R3. R3 is 5 ohms. R1 and R2. 5 ohms times 10 ohms. R1 plus R2. That's it. That's all the junk. And now it's just an issue of plugging it into a calculator. 10 times 10 is 100 divided by 15 minus 5. Then I'm going to divide that by 5 plus 50 divided by 15. .2 amps. Bam. So, I2, 0.2 amps. Now, I would like to point something out. You can think of the flow of current as though it's a vector. And we know from University of Physics 1 that if you choose the direction of a vector in a problem and you solve the problem, you end up getting a negative sign. What that meant was that you chose the direction wrong. Here it means basically the same. I2 is flowing through this, and since it's positive, we pick the correct direction. It could very easily be that in your analysis, one battery like B2 could be, you know, configured such that I2 flows the other way. And if that were the case, even though you're going clockwise around the loop and you're putting it as a positive, then the day when you solve for it, it ends up being a negative. And that's entirely okay. That just tells you about the direction, um, you know, uh, based off the assumptions and the rules that we're following here. So just be aware of that. So here we have I2. We got I2 originally by plugging in just junk right here into this, and plugging that into our equation here for number 1. Yeah, so let's just go ahead and find I1 then. I1 is going to equal to B2. B2 is 5 volts. I2 is 0.2 amps. R3 is 5 ohms. And then we're dividing that by R2. R2 is 10 ohms. Plug this into a calculator. I get 0.6 amps. So it looks like we picked the direction of that as well. So there you go. Here, this leg has 0.6 amps going through it. This leg right here has, 0.2 amps. Okay. So what that means is that our total current here would be 0.6 amps plus 0.2 amps, which is 0.8 amps. So the trick to using this loop rule is to stay true to the rules. Go clockwise, going from negative to positive across a battery like that makes the battery count as a positive. And then as your current flows through, you're eating up energy, so you're subtracting away the energy. And then when you pick another loop where you're going against the current that you've already established the direction of, if you're going against it, that adds in as opposed to subtracting away. So it's just a way of making sure that you follow sort of like conservation of energy properly, if you want to think of it like that. Okay. All right. So that's it for this video. We've covered all of Kirchhoff's rules, including the loop rule, and we've taken a look at resistor addition in both series and parallel configurations. Uh, in the next video, what I'm going to do is to talk about what happens when you mix components, specifically where you have a combination of a battery, a capacitor, and a resistor. And, some interesting things happen. And that's because capacitors act like air gaps. They're breaks in circuits, so current doesn't flow across them unless, of course, you decompose the dielectric. You exceed the dielectric strength, and you cause current to flow, which is decidedly not what we want to happen in a capacitor. So we'll talk more about that stuff in the next video, and I'll see you then.